Next, we're looking at the SN1 mechanism. This is, once again, substituted nucleophilic first-order reaction. So, that's going to be the first detail we're going to note about this. The rate is going to be equal to our rate constant times the substrate concentration. So the reaction rate is going to be fully dependent on that substrate. It is not going to matter what my concentration of sodium bromide is here. So this is going to be an SN1 mechanism. I'm going to have a propan-2-ol, just propanol, with sodium bromide. This will be a reflux. This bromine here is going to replace the hydroxide. Notice, bromine is not a better nucleophile. Bromine is a worse nucleophile than hydroxide. So why does this work? Well, here's the thing. The SN1 mechanism is going to be a two-step reaction that is going to have the rate-determining step be completely dependent on the substrate. The substrate is just going to lose its functional group. We're going to see that in a minute when we draw this out. But what this is going to give us is a two-step process. And that two-step process is going to proceed through a carbocation. Let's take a look at what this mechanism looks like. So, once again, I'm going to draw this out in a more detailed, exaggerated version that we would not normally do. So this is going to look like. So I've got my substrate modeled out here. My first step in the SN1 mechanism is this hydroxide group is going to leave. Okay, it's going to leave all on its own. Now, remember, there are collisions happening constantly here. So why does the functional group leave? Well, it's getting knocked around constantly. There's some stress on this bond, and this hydroxide is able to stabilize a negative charge. So this leaves. Regardless of the exact specifics, whether it's colliding with that bromine or that sodium, or it's in a solution that pulls this away and stabilizes it better, doesn't matter. The first step is this group leaves. Step is done. So, step one. And now we're on to step two. Notice, I am trying to be very emphatic that this group is leaving on its own before the bromine does anything. That is the entire step one. This is going to happen one after another, but it does not happen at the same time. So, our next part is I have a carbocation. So now I have a carbocation that is all by itself. Carbocation is an alkane that has a carbon that is holding a positive charge. This hydroxide group took that entire bond, and it's now stabilizing a negative charge. This is now the hydroxide anion leaving behind the carbon with a positive charge. Now, this bromine is very attracted to that carbocation, and that bromine is going to then form a bond with it. Now we have our final outcome. Our final outcome is the bromopropane. The bromine bonded into that carbon. However, while we have the carbocation, it's technically incorrect to draw this hydrogen like this because they're going to be spread out as far as they can, which means that this hydrogen is just going to be sticking straight out. Because of that, this bromine could attack from this side or from the back side. That bromine can attack from either way. And so what we end up with in this mechanism is we don't just have that bromine taking the place of the hydroxide. We could have an inverted stereochemistry as well. So we can have both, and we will actually get both in equal measure. Is that high enough? That is high enough. So when we have the SN1 mechanism, we are going to get a mixture of stereochemistry. Notice that is different than the SN2, where we exclusively got the inverted stereochemistry. Now, because we get a carbocation intermediate, this will tell us what we need to do to make this reaction work a little more smoothly. How can we encourage this reaction along? How can we ensure that we have a situation where this reaction is able to proceed? Well, we need to think of this in two ways. One, we need this hydroxide to be able to be away from that carbocation. It has to get far enough away that this bromine can attach before that hydroxide reattaches, right? Think of it this way. This hydroxide is a better nucleophile than that bromine. It's gonna try to reattach if it can. So that needs to be stabilized in some way, shape, or form. What's a way to stabilize a hydroxide or a lot of bases? Well, let's put them in a protic solvent. A protic solvent has that hydrogen binding that is able to surround that with a greater positive charge. This would be very stabilized in something like water or ammonia or some kind of alcohol. So if I did this reaction in water, it would very easily follow the SN1 mechanism because water is going to stabilize that anion. The bromine is not really going to interact with that hydrogen binding, so it's not going to hinder it from being able to attach here. So protic solvents, that's very important. Notice, the bromine is a weaker nucleophile. This is going to be very common. So the SN1 mechanism is able to proceed based on a weaker nucleophile. So weak nucleophiles are going to be favored in the SN1 mechanism because that stronger nucleophile is a lot more reactive. And the last thing that we really need to look at here is the barrier, the main barrier for the SN1 mechanism being able to occur. And we can identify that by looking at that two-step process, that second step. That second step is that carbocation. So our big barrier here is carbocation stability. That carbocation needs to be able to be stable in order to let the functional group leave, let that leaving group leave so that it can then take on a new nucleophile. So carbocation stability follows some specific trends. When we have something like a tertiary substituted carbocation, we have something like this. It's got a methyl group here, methyl group here, methyl group here. So we've got CH3. These carbons are all going to share that positive charge. And so this positive charge actually gets spread out between all four of these carbons. They're all related, they all spread it out, and so it's going to have greater stability. So tertiary substituted groups are going to follow the SN1 mechanism a lot better. Secondary groups are going to also be able to stabilize that, not as well as the tertiary, but still predominantly well. And those are going to be much, much better than primary substituted carbons. Primary substituted carbons are going to work so poorly for the SN1 mechanism that they're basically not going to happen. And methyl groups will not work well at all. So we can see this is in reverse for the SN1 mechanism versus the SN2 mechanism. This is why we're going to have a mixture of these two mechanisms. When we hit the secondary level, both are able to operate at kind of a normal reaction rate. And so we're going to get a mixture of SN1 mechanisms and SN2 mechanisms. But when we're at a tertiary substitution, the SN2 mechanism isn't able to operate because of that extra steric hindrance. That's the big blocker. That's the big barrier for the SN2 reaction. So SN1 is going to happen at a tertiary substitution. At a primary substitution, our SN2 is going to work perfectly because all of this room, all of this space to attack that substrate. But a carbocation is not stable at all when it is only in a primary substitution. It's going to be very reactive. And so a leaving group trying to leave this will immediately get reattached. So we're not going to see any SN1 products out of a primary substitution. So we can see this as kind of a guide right off the bat. Without looking at anything else, we should be able to tell if I've got tertiary substitution, I'm going to get SN1 products. If I've got secondary, I'm going to get SN1 and SN2. And if I've got primary, or even methyl, we'll throw that in there too, methyl, then I'm going to have SN2 products exclusively. So we can see a quick way that we can just look at our substrate and know which reaction am I going to be having. So next we're going to look at some examples. We're going to practice modeling out, drawing those arrows so that we can get comfortable with modeling our reactions before we look at our second type of reaction.